Wormholes are real. The cosmic tunnels, the shortcuts across the universe, the portals from every science fiction film you've ever watched, none of it. The physicists whose work inspired them never intended any of it. What Einstein and Rosen actually described in 1935 has nothing to do with space travel. A team of physicists just showed what it really means, and it's stranger than any wormhole. Time itself may flow in two directions, and the Big Bang may not have been the beginning. In 1935, Albert Einstein and Nathan Rosen published a paper studying how particles behave in regions of extreme gravity. They describe a mathematical structure, a link between two perfectly symmetrical copies of spacetime. They called it a bridge. It wasn't a tunnel. It was a mathematical connection designed to maintain consistency between gravity and quantum physics. Einstein and Rosen were trying to solve one of the deepest problems in physics: how to reconcile the physics of the very large with the physics of the very small. The bridge was their tool. Decades later, other physicists began speculating about what would happen if you tried going through one of these bridges. Could you cross from one side of spacetime to the other? Could you use it as a shortcut? The idea was irresistible, and the wormhole was born. But those same analyses made the answer clear. Within general relativity, the bridge collapses faster than light can cross it. You cannot travel through an Einstein-Rosen bridge. It's non-traversable. It pinches off before anything can pass. There is no observational evidence for macroscopic wormholes. There is no compelling theoretical reason to expect them within Einstein's theory. The entire concept rests on a misreading of a 1935 paper about something else entirely. So what was the paper actually about? A new study published in Classical and Quantum Gravity by Enrique Gaztañaga, professor of astrophysics at the University of Portsmouth, along with K. Sravan Kumar and João Marto, revisits the original Einstein-Rosen bridge using modern quantum physics. Their conclusion is that the bridge isn't a connection between two places in space. It's a connection between two directions of time. Most fundamental laws of physics don't distinguish between past and future. If you reverse time and the equations, the laws still hold. This is called time reversal symmetry. We experience time flowing in one direction, from past to future. But the equations don't require that. They work equally well in both directions. Gaztañaga's team took this symmetry seriously. They showed that the Einstein-Rosen bridge can be understood as two complementary components of quantum state. In one component, time flows forward. In the other, it flows backward from a mirror-reflected position. This isn't a philosophical preference. Once you exclude infinities from the equations, which physicists must do to get meaningful answers, quantum evolution must remain complete and reversible, even in the presence of gravity. Both time directions are needed for a full description of the system. In ordinary situations, physicists ignore the time-reversed component by choosing a single arrow of time. We pick forward because that's what we experience. But near black holes, or in expanding and collapsing universes, both directions must be included. The bridge connects them. This is where it stops being abstract and starts having consequences. Because if this framework is correct, it solves one of the most famous paradoxes in all of physics. In 1974, Stephen Hawking showed that black holes radiate heat. They emit particles, lose energy, and over immense timescales, they can evaporate completely. That result created a problem that has consumed theoretical physics for 50 years. If a black hole evaporates, everything that fell into it, every particle, every bit of information about every object, appears to be destroyed. That violates one of the most fundamental principles of quantum mechanics. Information cannot be lost. Quantum evolution is reversible. Every process can, in principle, be run backward. If black holes destroy information, quantum mechanics is broken. This is the black hole information paradox. Physicists have spent decades trying to solve it. Proposed solutions range from holographic principles through firewalls to entire new frameworks of physics. Gaztañaga's team offers a simple resolution. The paradox arises only if you describe the black hole using a single direction of time. If you insist that time flows forward and only forward, then yes, information crosses the event horizon and is lost. But if the full quantum description includes both time directions, nothing is lost. Information that enters the black hole continues evolving along the reverse time component. It leaves our time direction and re-emerges along the mirrored one. Completeness and causality are preserved. No exotic physics required, no new dimensions, no holograms. Just the full application of symmetries that were always in the equations. This framework connects to an even deeper possibility. If the Einstein Rosen bridge links two directions of time, then the Big Bang itself may not have been the beginning. In Gaztañaga's picture, what we call the Big Bang could be a bounce, a quantum transition between two time-reversed phases of cosmic evolution. A universe that was contracting reached a critical point and bounced, expanding outward as the universe we observe today. If this is correct, our universe has a history before the Big Bang. Not in the science fiction sense, not a previous civilization or a parallel dimension. A previous phase of cosmic evolution, related to ours by time reversal symmetry. Or basically a mirror. And there may actually be evidence for this. The cosmic microwave background, the afterglow of the Big Bang, shows a small persistent asymmetry, a preference for one spatial orientation over its mirror image. This anomaly has puzzled cosmologists for 2 decades. Standard models assigned it extremely low probability. But if mirror quantum components are included in the equations, the asymmetry is expected. The team goes further. Black holes could act as bridges not between distant points in space, but between different cosmological epochs. Some of the dark matter we detect gravitationally but have never directly observed could be made of relics from the pre-bounce phase. Smaller black holes that survive the transition and reappear in our expanding universe. I want to be clear about what this is and what it isn't. This is a theoretical framework. It makes predictions, the CMB asymmetry, the nature of dark matter, predictions that can be tested. But it hasn't been confirmed observationally. The honest position is that it's elegant, it's consistent, and it's testable. That's the most you can ask of a theory before the data arrives. The framework is built on established physics, general relativity, and quantum mechanics. It doesn't invent new particles or new forces, but it relies on a specific interpretation of time reversal symmetry that not all physicists accept. The standard approach in cosmology is to select a single arrow of time and work within it. Gaztañaga's team argues that this is an approximation, valid in ordinary situations but incomplete near horizons and at cosmic scales. Whether the CMB asymmetry constitutes genuine evidence for time reversal components is an open question. The anomaly exists. The interpretation is debated. Other explanations constitute of statistical flukes, systematic errors in the data, which haven't been ruled out, and the claim that dark matter could be composed of pre-bounce black hole relics is speculative at this stage. It's a prediction that future observation could tell us more, but it hasn't been tested yet. There's something poetic about the idea that Einstein's most misunderstood creation, the thing we turned into wormholes and time machines and Hollywood blockbusters, might actually be pointing to something deeper. Not a shortcut through the universe, but a mirror built into the fabric of time itself. No faster than light travel, no portals, no science fiction. Just the possibility that time, at the deepest level, flows both ways, and the Big Bang wasn't the beginning. It was a turn. If this one was worth your time, a like genuinely helps the channel grow. Subscribe for more of these. Thanks for watching. Clear skies.